Eftong, or Fort Nog, however you want to do it. So we've done those two. Acting which way on the box?
Acting upwards, or incline,
Up the incline. Good.
and on the ramp, downwards.
I assume you meant down the ramp. Tension, other? All right, so we've done the force diagram, check. The direction of acceleration, what is the direction that it will accelerate if it does accelerate?
Down the ramp.
Yeah, so my acceleration is in that direction. Magnitude of A and the direction indicated by the arrow. So now when we come up with our coordinate axes, this is why I prefer not to use X hat and Y hat, because the math people have brainwashed us so much of X, Y. I hat, J hat, hopefully will break some of you of this idea that everything has to be horizontal and vertical. One of my I hat direction, I'm gonna put in the direction of acceleration. And J hat, perpendicular to it. Now, whether it's going away from the ramp or towards the ramp, it depends on your mood. Anyone with a preference? So our coordinate axes have been defined. Now decomposition. Now I don't know if decomposition is really the right term, but it worked out in terms of the mnemonic. You're basically breaking it up into its components. So when we first were dealing with vectors, we added vectors, we did head to tail, got the Pythagorean theorem, found the magnitude of the hypotenuse, a little bit of trig, found the angle. Now we're going to go in the reverse process. So first off, we have to figure out what needs to be broken up. What gets decomposed? Given our I hat, J hat, which of these forces are not in plus or minus I hat or plus or minus J hat? Okay. That is the only one not in that, try that one again. It's the only one that is not in the I hat or J hat direction, plus or minus. So that's the one we need to break up. We need to break weight up so that we have components that are parallel to the ramp and perpendicular to the ramp, like we've defined here. So I have weight acting down. I'm going to break it up into a component going this way and one going this way. So for the typical stunning visual effects. That is a right angle right there. I need to figure out what that is, and I need to figure out what that is. I do know this angle down here, which I'm just going to label generically as theta, but 37 degrees. I know that weight is acting straight down, so that is a right angle right there. Right angle right there. So if this is 37 degrees here in this corner, what is this angle? Or how would you find it?
Because the sum of all angles has to be 180.
Okay, and I know that one's 90 degrees.
And we know that one's 37 degrees.
Yep, that's 37, so that one would be 53 degrees. 53 degrees. I'm going to label, I don't think it's standard math notation, but I'm going to label the complement as theta prime. So theta plus theta prime is equal to 90 degrees. I know that my weight, this black arrow, is perpendicular with the ground. So what is this angle right here?
37.
Yeah. So that is going to be theta right there. So as I'm looking at this triangle, I now have a right triangle where I know one of the angles. That's my hypotenuse there. That is theta. And now I need to figure out the opposite side and the adjacent side. Now, it doesn't, apparently I can't draw. I'm not sure that's much better, but that's supposed to be closer to a 90-degree angle there. So if I'm trying to find the opposite side, is that sine or cosine?
Sine.
And so this is going to be the weight times the sine of theta. And this one would be the cosine of theta. I'll do the intermediate step for those where trig is either lacking or weak. Again, I have a right triangle here. I have an angle theta and I have my hypotenuse. I'll just label this as M and Q. I know that the sine of theta is equal to the opposite over the hypotenuse. Solving for M, which is the opposite length, it's going to be W times the sine of theta. That's bad notation. So M equals. The adjacent side, I know the cosine of theta is equal to the adjacent side divided by W. And therefore, the adjacent length is equal to W cosine of theta. Another way that you can do this, so let's say that you're in a test, your trig is, and suddenly your mind blanks. What do you do? Well, you could take the random guess, as some students have tried in the past. But you could also, if you try to draw it to scale, so all my angles look like 45 degrees when I draw them, or most of them do. So what I'm going to do is I'm going to try to draw something that is clearly less than 45 degrees. That's 37, less than 45, unless the math people have lied to us. So I'll draw my line, I'm going to draw something that's clearly less than 45 degrees. I'm now going to draw my weight vector, which is coming straight down. I'm going to break it up into two components. I have this component down the ramp and this component perpendicular to the ramp. That's a 90-degree angle. And so now that I've done it this way, I have two components here. One is clearly bigger than the other. This one is bigger than that one. So if you're panicking and you know one of them is cosine and one of them is sine, you can just do both of them, and the bigger one is going to be this, and the smaller one's going to be that. Now, if I'm bigger than 45 degrees, it'll flip. But if you try to draw it somewhat accurately, you can get a pretty decent guess at it. Questions to hear? So I am making the claim that this force diagram here can be also written as I have friction acting this way, I have normal force acting this way, I have the weight times the sine of the angle down the ramp, and weight times the cosine of the angle into the ramp. That this and this are the same thing. Because if I add those two together, I get that. So now, we've decomposed. Brian, you have a look on your face like you have a question about something.
I don't think I
Sure you don't wanna ask?
Wait, but why wouldn't the sign be on the J hat? Why is it?
Why would it?
Because isn't
That's what we're breaking up into that's the right triangle we're working with. If that's a 37-degree angle there, that's a 37-degree angle there. The opposite is sine.
okay. Yeah, I get that.
Other questions? After decomposition, we have equations of motion. We have two equations of motion, because I have one object, 2 dimensions. Again, equations of motion. Our template is F equals ma, so I'm gonna have all my forces on the left-hand side, equals mass times acceleration in whatever direction it is. Let's take my I hat equation, in a color that might show up better. So we want to take a shot at the first equation.
Weight times the cosine of theta.
So you're doing J hat, okay. Weight times the cosine of theta.
Minus y equals m times 0.
All right. The other equation?
Weight times sine theta.
Let's see, different voice. Give someone else a chance to show off. Oh, don't make me go back to Ethan again.
Weight times sine theta minus friction equals mass times acceleration.
Done. 2 equations. We know mass, and we know theta. Those are the 2 that we know. Substitution. Do we have an independent formula for any of these variables?
For weight.
And what is the formula for weight?
Equals y
mg
yeah, equals
equals mg.
Mg. Yeah, you were jumping ahead. This that might sound like. So this equation will be mg sine theta minus the friction is equal to mass times acceleration. And this one is mg cosine theta minus y equals 0. Now the solving phase. I do need to give some location here. Why don't we put this on, actually we'll wait, but we'll wait to plug the number in, but let's put this on Earth 1. Where I'm setting little, Earth 1, little g is 9.8 meters per second squared. All right, so questions before we actually start solving in more detail. Kelly?
This might be a dumb question, but
Yeah, go for
why
it.
is m in both equations?
Because the formula is force equals mass times acceleration.
So is m always in both equations?
Yes, but in this case, since I'm gonna multiply times 0, that this mass is irrelevant. At some point, I'm gonna stop writing mass times 0 and just write 0. Is that?
Yeah, I just need to like go home and lower, and then I'll be fine.
Okay. I don't know. Maybe this helps, maybe it doesn't. I did skip a step because generally it's a nuisance to do, but perhaps this will clear it up somehow. If I just plug straight in here, didn't worry about I hat, J hat, two equations with I hat, J hat. Technically, what I would get there is I have W sine theta I hat minus Y J hat minus F I hat plus W cosine theta J hat is equal to mass times acceleration, which we've already established is in the I hat direction. So that's my acceleration right there. That's plugging F equals ma. Plugging, these are all the forces, all four forces, counting that as two forces, is mass times acceleration. To solve it, I basically separate it into the I hats and the J hats. So if I have only I hat on the right-hand side, since I hat and J hat are perpendicular to each other, I would do W sine theta I hat, that one's taken care of, minus F I hat, that's supposed to be an I, equals M A I hat. So those are my I hats. My J hat equation is this, so I have negative Y plus this one, W cosine theta, is equal to, well, I don't have any J hats on the other side, so it's 0. No, sorry, J hat, J hat, J hat. And since I hat's in every single one, in a sense, you could factor it out, and what we're left with is, well, that equation. And here we can factor J hat out, and what we're left with is this equation. Not if anything looks, or many, not, basically I don't think that helped any, but
Now the move worse.
slightly more formal, but in the end, you're breaking it up into an I hat and a J hat equation. All right, let's actually solve. Let's assume for this round, friction is equal to 0. So frictionless, I can do a shorthand for frictionless. Instead of writing friction is equal to 0, I can write mu sub k equals mu sub f equals 0. That's just shorthand for saying it's frictionless. Officially, that's the coefficient of kinetic friction, coefficient of static friction equal to 0. That's the same as saying it's frictionless. So that means my first equation breaks down into W's, got past that already. Mg sine theta is equal to Ma. At this point, you might notice that I have M in both terms. I can cancel it out. I can divide it out by the M's out, and I get G sine theta is equal to the acceleration. And so therefore the acceleration, 9.8 times sine of 37 degrees. And so the magnitude of my acceleration is 5.9 something, 5.88. And then, let's not forget units.
Meters per second squared.
All right. It's as simple as that. The dramatic pause was for questions, in case someone had some. All right. You know, frictionless is well and good, but the reality is there is definitely friction. Actually, friction is rather crucial in some cases. You wouldn't have toast without friction. Actually, you wouldn't exist without friction. So, let's throw friction into it. So I did mention that there's two types there. There's static friction and kinetic friction. We symbolize them very cleverly with a subscript K for S. That's an N. And it's static. For those who have not had physics, actually, who's had physics before? All right. For those who have not had physics before, what do you think the difference between kinetic and static is?
Static involve electricity?
No, there is a relation from the word static there, but no, not electricity. Wait, static is
Like still, and then next moving.
pretty much kinetic moving, static not moving.
That's what
And a static charge is a charge that is not flowing from one object to another, we're just sitting there waiting, stasis, waiting to be discharged. Usually when I touch the outside of my car. All right, so we're dealing with something that's moving, kinescope, kinematics, kinesiology, the K-I-N-E Greek root, meaning movement, and static. I'll assume it's from the Greek also. If not the Greek, the Latin. If neither of those, Shakespeare or the Bible. So we have this friction dealing with an object not moving, and friction dealing with an object is moving. This is the most prominent theory. I'll explain why there are other theories to this.